In synthetic chemistry, the most common reaction of benzene is electrophilic aromatic substitution. It is based on the idea that the benzene ring has a lot of electrons, it has high electron density, and it attracts electrophiles. The mechanism for this case follows an addition-elimination mechanism. First, the electrophile is added to the ring and breaks one of the pi bonds, forming a new sigma bond. Here you have a carbocation, and this carbocation can be stabilized by several resonance structures. Ultimately, this proton can be taken by a base, and the double bond is again reformed to form a new compound wherein your E is now the new substituent. Thus, this process involves an addition and an elimination. The carbocation formation in this process is part of the slow step or the rate determining step. First step, formation of the carbocation, is the rate determining step, and the second step is the faster elimination part. Overall, you start from an aromatic ring which contains 6 pi electrons, and in the end, an aromatic ring still remains. So, aromaticity is preserved in this process. Since the first step is the rate determining step, if the electron density of this ring system is increased, then it will be more reactive to electrophiles, and the rate will increase. Thus, high electron density in the ring leads to faster rate. And so, we have established several reactions under electrophilic aromatic substitution. These reactions will be discussed in later slides. The first reaction is halogenation. Halogenation uses halogen, such as Cl2, and a loose acid. The mixing of ferric chloride, for example, and chlorine molecule forms Cl+. If you want to form Br+, then mixing of bromine molecule and ferric bromide is required. An example, you have a benzene ring, which is reacted with chlorine and aluminum chloride, will produce chlorobenzene. If you use the alternate bromine molecule and ferric bromide, we will produce bromobenzene. Fluorination is so rapid, it is hard to stop at monofluorination. An alternative procedure is used if fluorobenzene is required. This procedure is part of the amine topic. Iodination uses an alternative reagent system, such as iodine and nitric acid, or N-iodosuccinimide, or NIS, and sulfuric acid. This reaction will produce iodobenzene. Next is nitration. The reagent for nitration is concentrated nitric acid and sulfuric acid. This mixing will form the NO2+ species, which will act as the electrophile and react to the aromatic ring. Thus, you will get nitration and form nitrobenzene. In the case of sulfonation, it occurs most rapidly using fuming sulfuric acid. Fuming sulfuric acid is concentrated sulfuric acid with dissolved sulfur trioxide. Sulfur trioxide is the reactive species, and oxygen, being very electronegative, will pull electrons towards itself, giving sulfur a partial positive charge, and thus it will be attracted to the ring system. You should note that sulfonation is an equilibrium process, and thus the fuming concentrated sulfuric acid will allow sulfonation, but dilute sulfuric acid will remove that sulfonate group. The next type of electrophilic aromatic substitution is called Friedel-crafts alkylation. This named reaction uses an alkyl halide in the presence of a Lewis acid, such as aluminum chloride or ferric chloride. You can use several alkyl halides. Here I use methyl chloride and aluminum chloride reagent system, and it will give you methylbenzene or toluene. Now the reactive species here is a methyl chloride in complex with the Lewis acid. As I mentioned before, methyl carbocations and primary carbocations are difficult to form, and so partial positive carbons are much more likely and act as an electrophile to give you the alkyl benzene. One thing you should consider in this case is that a carbocation may be formed, and if a carbocation is formed, then rearrangement is possible. In this example, I used 1-chloropropane. Now in the presence of the Lewis acid, aluminum chloride may take this chloro group and form a species in which there is a greater chance of the formation of the more stable secondary carbocation. Thus, when 1-chloropropane is reacted with benzene in the presence of aluminum chloride, this compound is the major product. This compound is commonly called cumene or isopropyl benzene. Any reaction system that forms a carbocation can be used to alkylate an aromatic ring. For example, if you have cyclopentene in the presence of an acid, it can readily form a cyclopentyl cation, and the cyclopentyl cation can react with the ring system to give you this compound. Aryl and vinyl halides cannot be used because the formation of carbocations in this type of compounds are difficult, if not impossible. Next is Friedel-crafts acylation. Similar to Friedel-crafts alkylation, it requires Lewis acids, and in this case, acid chloride or acid anhydride. I use here an acid chloride and the Lewis acid aluminum chloride. Again here, aluminum chloride will take the chlorine atom and leave a positively charged species we call the acylium ion. The acylium ion will react to the aromatic ring to give you this compound. Take note of the position of the carbonyl group. It must be right next to the ring system. Once you are able to place substituents on the benzene ring, these ring substituents can later affect the reactivity and radioselectivity of subsequent electrophilic aromatic substitutions. If nitration of these three compounds is desired, you will notice that they have different rates of reaction. Toluene has the fastest rate of nitration, followed by benzene, and the slowest rate can be observed for nitrobenzene. Why is this the case? Substituent groups may withdraw or donate electrons to the ring via inductive effect or resonance. As I have mentioned earlier, higher electron density on the ring can increase rates. Thus, if you increase the electron density of the ring, the rate will increase. If the electron density of the ring is decreased, the rate will decrease as well. There are two ways that electrons can be donated or withdrawn from the ring. It can be by inductive effect. Inductive effect is a field effect wherein a group can pull electrons via the sigma bonds, and this is affected by distance. Another is by resonance effect, wherein a group can donate electrons or withdraw electrons from the ring via the pi system. Resonance effect is not affected by distance. And so in our case, toluene has the highest rate of nitration, given that the methyl group can donate electrons to the ring by hyperconjugation. And nitrobenzene has the lowest rate of nitration because the nitro group is known to be an electron withdrawing group. It can withdraw electrons by resonance effect. Thus, we have two types of groups. We have electron donating groups. Electron donating groups increase electron density of the ring, and they are activating. The rates will increase when they are present, and they are called ortho-para directors. When an ortho-para director is present on the ring, the next substituent are mainly attached at the ortho and para positions. This is because, for example, once your electrophile forms the initial bond to the ring and a carbocation is generated, if the ring substituent is at ortho position, for example, if it's attached here, it can stabilize that positive charge directly by electron donation. Halides are also ortho-para directors, but are mildly deactivating. Example is chlorine. Once you have your chlorine and you want to add another substituent, such as a methyl group by Friedel-crafts alkylation, the methyl group will preferentially be added at the ortho and para positions. Here I show the addition of methyl group at the para position. Take a look at the location of the positive charge. This positive charge can further delocalize to form a positive charge at this carbon right next to chlorine. Chlorine can then allow its lone pairs to be donated to the ring to stabilize this positive charge. In this case, an ortho or para addition should give lower energy, and so is more preferred. It also means that strong electron withdrawing groups are the activators. They pull electrons from the ring and make the rates of reactions slower. They are meta-directors. Based on this, we have classifications of ortho-para directors and meta-directors. Take note of these groups. Most of them are electron donating groups. And these are meta-directors. They are deactivating groups because of their electron withdrawing property. Another thing to note about ortho-para directors, and most of ortho-para directors anyway, is that the atom that is directly attached to the aromatic ring usually contains lone pairs of electrons. We have nitrogen, which has a lone pair, oxygen, which has a lone pair, or even the halides. All of them have lone pairs. Halides are deactivating because halides are electronegative. They pull electron towards themselves, and so they reduce the reactivity of the ring. But they also have lone pairs that can stabilize the carbocation intermediates during addition of a substituent at the ortho and para positions. If you have a strong activating group, for example, you have an amino group and a hydroxy group, they may cause the aromatic ring to be so reactive that there can be unwanted reactions that take place. For example, for phenol, if you do bromination in water, bromination can occur at both the ortho and para positions, and it's difficult to stop at an intermediate stage. Nitric acid can oxidize reactive aromatic rings under the nitration condition. The ring is destroyed, so we cannot do nitration of aniline and phenol. To avoid this problem, we can do a protection step. The amino group, for example, can be protected by an acetyl group. Acetylation converts your amino group into a more mildly activating acetamido substituent, and subsequent electrophilic aromatic substitution can be controlled quite easily. Here, the acetamido group containing your nitrogen directly attached to the ring is also an ortho-para director. So you can expect the product to be an orthochloro and a para-chloro derivative. The acetyl group can later be removed by heating in an acid. A sulfonic acid group may be used as a blocking group to force ortho-substitution. So if you have a sulfonic acid group at para position, this position is blocked, and successive electrophilic aromatic substitution for the case of toluene can only occur at the ortho position. There are procedures wherein you can control the substitution of a sulfonic acid group. Now, the sulfonic acid group can be removed again by mixing with dilute sulfuric acid. Groups may provide reinforcement to direct the next site of electrophilic attack. Strongly activating groups generally win out over weakly activating and deactivating groups. Small difference leads to mixtures of products. This is the rough sequence of activating property or substituents. For example, if you have this compound, M-nitrotoluene, and you want to add another substituent by electrophilic aromatic substitution, which substituent will direct the next site of addition? In our sequence, the alkyl group is here and meta-director is here. So alkyl group will win out. It will be the directing group. The addition will be at para and ortho positions relative to the methyl group. How about this one? We have here a methyl group and a chlorine atom. In our sequence here, you have methyl group and the chlorine atom is here. So the site of attack must be at the ortho position of the methyl group. That will be the major product and not at the ortho position relative to the chloro group. There is little substitution that occurs between two groups that are meta to each other. Only 9% substitution can occur between methyl and chloro groups that are meta to each other. This is because of the crowding around this area. It's easier for the attacking species to be attached at these much more open locations, and so 59% of substitution will occur at this location, ortho to the methyl group, and 32% substitution at this location, which is para to the methyl group. Regarding alkyl benzenes, oxidation of the alkyl side chain by hot potassium permanganate in the presence of a base, and then an acid workup leads to benzoic acid. It can occur with any alkyl side chains, can be methyl, propyl, isobutyl, or even the acyl type groups. In hot potassium permanganate and OH-, followed by acidification, all will produce benzoic acid. It will also work for this type of compounds. And take note that T-butylbenzene does not react. Free radical halogenation of alkyl side chain occurs on the benzylic carbon. The benzylic carbon is this one, carbon right next to the aromatic ring. And if you use N-bromosuccinimide or NBS, you will need peroxide or lye. This is the solvent. Bromination can occur at the benzylic position. This is because benzylic radicals and cations are stabilized by resonance. Alkyl groups are ortho-para directors in electrophilic aromatic substitution.